Hello, everybody. This is Robert Fretz from Switzerland. I have the honor to talk to you about biotech production plant automation and digital integration. A successful implementation which has allowed the company Roche to produce medicines like Avastin for over 10 years now. So I will organize my speech into several chapters. I will first start with my integrated view of process automation in a manufacturing context, then go through biotech automation in a first overview. Then this is composed of three main components, DCS, MES, and historian, of which I will go through next. And then we'll talk about how everything works together, and finally how we build and qualify it. So let's start first with my integrated view of process automation in the manufacturing context. So when we are automating a biotech production plant, we are not just automating a process or equipment, we are automating actually a business. And this business can be divided into specific steps, which I have denoted here as plan, prepare, instruct, operate, collect, report, analyze, and release. To make this more clear, I have put this in a picture. So in this picture, we have the equipment here at the bottom, and typically the material flows through the equipment from left to right. So we start with planning. We plan what product we want to produce, in which time frame, in which quantity, and on which piece of equipment. And we prepare these units, and not only the units, but also information like recipes, and make sure we have a master batch record ready to then collect the data into. Then we would have to instruct the personnel and make sure we have all the procedures and trained people to actually operate the plant. When they really operate the plant, they during this time, what happens is that all values, checks, events are recorded. These recorded values are then put into a report, which contains the batch record itself, but also highlights any exceptions that would show us where the process was not within pre-established limits. We can also analyze these data to see whether we were in time, if the quality was okay, and some other metrics like energy consumption. And then we can finally release the product. So this is the whole process as I see it, as one thing, and try to automate equipment and business together. And digital transformation is also about understanding that each of these elements of this business processes has data attached to it, and these data can be meaningful to improve continuously our production. So in our world, these functions have to be executed in certain systems. And these systems as an example here are the ERP, Enterprise Resource Planning System, where scheduling, training management, maintenance management may happen. The next piece of equipment that we are using is obviously process and equipment control. So our temperatures and flows and pressures are all right during production. And all the middle part, prepare, instruct, reporting, is executed typically by a manufacturing execution system, MES. And for the release, we also normally get help from LIMS, Laboratory Information Management System. Now, this is a standard setup for many sites over the world. when you say standard, you think this is static, but that's not true. There is tremendous evolution going on in this area. Digital transformation is impacting all these systems. And some of these trends I would like to highlight here. So strongly impacted areas are like sensors, for instance. We started with measuring a single value. Today, most instruments can get multiple measurements. Then when we had to adjust the instruments, we had to really go to the instruments, do everything there. And what we done there was then fixed until we went there the next time. Today, we can change, adapt anytime from remote, most of the instruments that we have. Then in the old times, we had only limited information about the sensor's health. Today, we can continuously monitor their status. So this is a great improvement in the area of sensors, and that's driven by something that's called IIoT, Industrial Internet of Things, that help us improve all this sensor business. Next area where we have a big improvements is communication. Before we had one wire with one value that carried a certain current or voltage. Today, this wire is a network, and not just one value is coming, but a whole stream of data. So it's obvious that the internet is driving this. For presentation, before it was difficult to have some display from different systems on the same screen. Today, this is really easy with the dynamic displays that are provided by web technology. So also many vendor-specific solutions are now transforming into generally available standard technologies. So it's easy to match and mix vendors and technologies and still make it all visible to the operator on the same screen. Then another advantage we have is in control logic. For a long time, a single loop PID control was about the best you could do, but now we have multivariable control networks, which can be easily constructed through the control software. And we had fixed settings. Today, we can have continuously self-tuning algorithms, which really helps to stabilize our plants and get better and more control over our process. So the process industry, which was something separate and special for a long time, is now moving towards web and networking, and that from the sensor up to the enterprise level. So now I would like to give an overview over biotech automation and digital integration. So let's first look at production plants. So we have normally 4 areas. We have inoculum, where we start with the seeds, and then from the seeds, we go into always large scales. I show these by the number of X's is here. Where fermentation then really makes the actual product. But this product is in a mix, so it has to go through a purifying process before it finally can be filled in some API carrier, which is typically in the biotech industry is cooled to like -70 degrees C. So these 4 steps form biotech production in a general way in a steel plant. And I'm now talking about most of the area is fermentation, where the main thing happens. So these plants are controlled with a number of systems. While this picture may look complicated in the first place, It's actually composed of three main parts. One is the DCS, the distributed control system, which is controlling the equipment and runs recipes to execute the process. The second main component is MES, which is done to mostly to make sure we have a batch report. It has set point values, it compares and can tell us about any exceptions. Also, it looks especially at weigh scales and handhelds to input data for things that happen manually in the process. And then we have a third component, the historian, is normally used because I come to this a little bit later. The DCS itself does not really store data for a long time. So these systems have to be put together somehow to be able to work together. So they run on real systems, which in the old times always was dedicated hardware. Today, digital transformation can be helpful in the sense that some of these systems don't need separate servers, but can be virtualized in big data centers, which makes their operation more efficient. So systems are networked. So on a typical factory setup, we have a plant network where all the DCS, building automation, utility automation, environmental monitoring are connected and then talk to the so-called plant historian. On the other hand, we have systems like MES and LIMS, which also normally connected to the plant network. But in our factories, we also have an office network and enterprise systems. And we connect these systems through so-called firewalls, where we can exactly control the traffic, so we can guarantee secure operation even if everything is connected. So now I would like to go through these three main components, DCS, MES, and historian, and I start with DCS. In DCS, we look at the plant and try to organize it so we can control it. So the first type of organization is that we divide the plant into so-called process units. So we say we just look now at one fermenter, and we try to automate this fermenter so that it works in itself. And then we can also repeat this design for any fermenter that we have. It's also a question of efficiency of engineering and building a plant. Around the fermenter, we have so-called equipment modules. So an equipment module carries a certain functionality like transfer in, solid supply, heating, cooling, agitation, pressure control, gas feed, pH control, or transfer out. So these equipment modules, they are composed of hardware and software. And the whole process unit is composed of just a piece of main equipment and a number of equipment modules. Now, what is an equipment module? How do we organize that itself? The equipment module is actually the one that carries the controllable functionality for processing, which contains also pumps, pipes, valves, etc. Then it has these elements, also carries the functionality for automation with sensors, valves, and then behind it some control logic. A module typically belongs exactly to one process unit, so we can stay within these boundaries that we have here. So this is like a separate room. And then the exceptions to the rule of belonging to exactly one process has to be broken for something, for modules that we have in transfer piping, because if we wouldn't do that, it would really complicate the design. So the module carries the functionality. This can be defined with some specification, like today in this heat-cool example, we say we want to control the inner batch temperature of the reactor. And we can apply the set point in steps or in a ramp, etc. When we reach a limit, we will switch to cooling to save the product. An equipment module is typically controlled by parameters, values that come from the recipe, like the temperature set point, the maximum temperature that's allowed. Do you want to ramp up to this set point slowly or with a certain speed, or do you just want to jump more or less to the new set point? So all these values change over time coming from recipe, and that is how the whole plan can be operated, applying parameters to every single equipment module. Now, in the case of transfer, as you see here, we have a lot of fermenters that are somehow connected. There's not a one-to-one piping, but a piping system that allows us finally to transfer material from, let's say, top right to another one, requiring then some of these transfer equipment modules to be activated. And during this time of this transfer, they will belong to one. They will be added to the list of equipment modules of one process unit, and at the end they will be released again. And an equipment module can be booked by a process unit only by one at any time. So with this we can organize the transfers. We apply this also in software because to organize software sometimes you can be quite chaotic if you don't organize and have a good design. So we organize our software into first recipe operations and then libraries. Recipe operations have to do with the actual production, transfer, fermentation, discharge. Libraries, on the other hand, are repeating processes for cleaning in place and sterilization in place or sampling, which are not actually producing, but are necessary to make production possible. We have three types of function blocks that are combined into the software of a process unit or recipe unit. So we have the modules, including the equipment. We have recipe operations, which contain modules, and we have libraries, which also contain modules. And for a certain process unit, we put that together into one piece. And all these processing units are executed to run a recipe and make a production of a certain product possible. So how does this now work when we produce? So every unit, like every fermenter, for instance, runs on an independent sequence. So you can imagine that when we produce, unit 1 goes here through from top to bottom. Just do like this. We do sterilization in place for the unit and for the pipes, then we transfer water, we put the solids in, and then we mix and temp control at the same time as we do some sampling. When that is done, we go to transfer out, and then we clean the pipes and clean the unit. So this operation runs also independently on unit 2. There are times in which we have to think about how can we coordinate them, because this time is typically at the time of transfer. So if this unit 1 is to transfer out and unit 2 is to transfer in, somehow they must be in these phases at the same time. And we do that using specific transfer logic in the transfer out and transfer in equipment modules to do this specific synchronization. I will show this in the next slide. So just assume we have unit 1, which at this time is in mix and temp and sampling, producing something. And so this is this unit 1. And we have unit 2, which is still in preparation. It's not ready yet to receive material. So at some point in time, unit 1 will be done with the mix, temp control, and sampling, and move to transfer out. That is when this transfer logic of unit 1 will be activated, and it is looking out for a partner. It now needs a place to send its material to. While unit 2, it doesn't know who is its partner at this time. Now, unit 2 finally moves from preparation to transfer in and activates its own transfer logic that also looks around for a partner. And they will finally find each other. And when they're synchronized, the transfer can take place. So this transfer takes some time. When it is done, we can switch it off, and each unit again goes a separate way, like unit 2 is going to fermentation. So it's fermenting, while unit 1 has activated cleaning for the pipes. So with this mechanism, we can run independent sequences for all units and only synchronize, and we don't need a full overall program to control everything from a central place. So I would like to summarize the software components or all the components of process automation and the DCS part. So we have modules which contain hardware and software. Then we have recipe operations, libraries which contain only software. Libraries and operations are normally combined into master recipes, which we can reuse for a certain batch when they are copied to so-called control recipes. And what we also have are so-called formula sets of values that we can then apply to the master recipes. So the recipe operations and libraries are built of modules, and the master recipes are built of recipe operations and libraries. Now, this concludes the DCS part, and I would like to move to MES. Now, why do we need an MES in the first place? So we have heard what the DCS can do. It deals with continuous control, automatic sequences, with recipe management. But it also does not store a history at the meantime. In the opposite, MES supports production planning, manual operations, material management, electronic batch reporting, and every transaction is recorded. So we have this area, which is these two areas which have a different type of operation. Now, what are the operations that MES specifically supports? They fall into a number of categories like planning, execution, and quality. So execution would be weigh and dispense. This is taking bulk material from the warehouse and dividing it into small portions that can be applied to the process. Then we have small quantities management, material tracking. It will know the way a material went until it was consumed, filter testing, and especially one special thing is DCS interaction, because MES and DCS will have to work together. Before I go to that, there are some common libraries that are components which are used to build other quality functions for applications for MES, like sampling, room monitoring, or reporting. So how do systems work together, DCS and MES? Now let's assume we have a DCS phase, and phasing, and one phase is that new filter has to be built into a piece of pipe. So what happens is when this is activated, we would tell the operator on the screen, oh, there is a MES action required. At the same time, the MES knows that it has to activate this filter activity. Actually, it's going through this new filter function. And the operator, when he gets here, he will be able to go through a number of steps, operations that it has to do to identify the filter, to exchange it, to build it in. And finally, it will come to the last operation, like confirming that everything went okay. When it does this confirmation, we will tell this function that we are done. And this goes back to the DCS. And the DCS can then go on with its own activities. So we also try to just have one single point of connection, but not an overall program for both. So with this setup, we can run MES and DCS together. I come to the third big component of systems for automation of a biotech production plant. This is the so-called historian. So what is the problem we want to solve? First, we know that the DCS does not store really a big history. The MES on itself produces a full electronic batch record, EBR, but only on its own activities. So what we use the historian for is to make the DCS data available to MES so we can produce finally one report. The historian, in addition, also collects data from additional systems, not only from DCS, but also, let's say, from environment monitoring or room monitoring and or utility monitoring. And we can add these data to our report. So what we do is we just take all process data because they are not recorded typically here and put them in plant data storage from DCS and building automation, utility automation, and or environmental monitoring. So also all these systems in the lower part, their data are also available, as are all MES data, which are typically stored in a relational database. So now we have these data coming from these systems to the historian. And when the data come, they're just numbers, but it is really more a process. So we send all data here to the historian, it records in real time, and it keeps process data for unlimited time. Historians, here technology, also digital transformation, has helped us in providing ever bigger and bigger space for data storage. So in addition, the data historian adds context to the data coming here, like in which equipment, which batch number was running, and other things. Also, the historian can calculate additional data from the values it receives. And you can look at the data in so-called time series data by batch shifts, easily filter it out. Every consumer of any type of process data is reading just from the historian, and therefore we have something which we call here one version of the truth. So historian has additional benefits, which I would like to highlight. It's more than just numbers. We get the numbers in a context, as I already mentioned. Context can be equipment information, batch information, environment information. Then also we can look at the data in an object-oriented way, which means we must not know the exact name of a temperature sensor. It's enough for us to understand we want to look at bioreactor number 1 of its main inner temperature. So this helps to make the process more transparent. Also, a broader audience can look at the data. Then another big point of the process data historian is to provide many-to-many communication. I will show that in a minute. And then in addition, it's a tremendous source for any type of analysis, not only for quality or compliance, but also other metrics about performance. You can compare performance of different batches, and you can do time studies. Also, what is very helpful, because we are typically evolving and improving our plans continuously. So the process data historian is very robust in taking in new requirements and accommodating them without disturbing the things you already have in there, which is very important for a stable production. So now, how does this all work together? So integration means communication. So we must be aware that many systems have to communicate with many systems. And it would be very difficult to build an interface between all systems that the number of interfaces would explode. So, but examples of communication. MES uses data from building and automation, DCS, environmental monitoring, LIMS, training management, ERP. So it's like a spider. LIMS uses data from MES. Deviation management uses data from MES, LIMS, and DCS. If you want to put a batch report together, you have to use data from DCS, MES, and all the other automation systems. And then finally, ERP will use data from MES for materials management to know how much material was consumed, how much material was taken out of storage, etc. So to give you 2 examples of this communication between, let's say, between ERP and MES. ERP will have to provide to MES with material master data, what type of materials we have, and also will provide the MES with production order. In the other hand, MES will report to ERP what type of material consumptions were performed and how much material and what material was produced. For communication between DCS and MES, we have this, what I already showed, the MES workflows that are triggered by DCS and confirmed if the workflow is completed. So which tools do we use to do this communication? So look at the data where they are. So in MES layer, we have typically a relational database. And in the communication between DCS and the automation system is typically done by a technology called OPC. So this is a standard protocol that allows data to be sent from any of these systems to the historian. Now, for relational database, we are typically using so-called web services. You could also communicate with relational database directly by using their standard language, SQL, but that is a very dangerous thing because you must have control over what type of commands are given to your database. And with a web service, you can always control what type of communication you have to the database itself and have some isolating layer between the outside world and your database, so you can guarantee the integrity of it. So I would like to give an overview of all this data flow. So all process units continuously send process data to the historian. These data include values like batch ID, phase numbers, names, and when they change. At the same time, also the supporting systems are continuously sending data. MES activities happen in parallel at the same time and produce a batch report. So when the right time has come, the MES can require this reporting web service to collect data for a particular batch. It collects and groups the process data from the historian for the time frame of the batch and adds header information, material information, and deviations. These data are then sent to MES, and MES integrates the data into a batch report. So you have one report for all process units, including separate MES activities. Production can then analyze and approve the report, one report, and send it to QA, and QA can analyze and finally approve the batch report, and the batch can be released. I'd like to put this in a picture. First, we see these types of communication from ERP to MES. We typically use something called iDocs if the ERP is from a brand called SAP. And we have the OPC communication between all the systems that control the plant, including set units to the data historian. The data historian can send data to MES via web service, and the final report can be sent over HTTPS to produce a batch report, all in one place and no paper. So I'd like to show this in a bigger picture. As this is complicated, I will go through it step by step. So first we have batches running in parallel to all the supporting system continuously sending data to the data historian. So the batches are batch data are collected in the historian. In parallel, we typically have MES activities as shown earlier, like exchanging a filter or other activities, taking a sample. And these activities self-produce the batch report inside of MES. Now, when the time has come to ask for the final data, when a batch is more or less finished, we can then ask MES to activate the reporting service, web service, which brings data and adds them to the already existing batch reports of MES. This batch report, we can take and analyze it and say, okay, I like it. That's really what we do, and send it to the next session, which is QA, which then they do their analysis. And then when they are happy with it, they can release the product, and the product can be used for distribution. So that's the full picture. Now, all this has to be built and qualified. So how do we do this? We follow a so-called GMP, good manufacturing practice approach, in some clearly defined life cycle steps. These steps are specify and design, build, then test, then implement and use. The completion of each set normally requires a review. So we know, okay, we have done everything that's needed here before we are going to the next step. Reviews are obviously documented. And to do this, we use two different approaches. For MES and Historian, which are, let's say, pure software, we can test this at the vendor site with a FAT, factory acceptance test. And then we can verify the system when it's implemented on site. This includes compliance with Part 11, like electronic fitness for electronic records and electronic signatures. The second method is used by the DCS because it includes equipment, sensors, wiring. We have to do everything on site. So I show this process now for MES and Historian. We start with CSV, computerized systems validation, with something we call the extended V model. So this should be our letter V and extension. So we start with specify and design. Normally, we have a user requirement specification at the start to tell us what do we need. Now, this user requirement specification is typically unaware of a specific system that has to be transferred in a system specification when we know it's for system A, B, or C. Then, when we know we have the system and we have the specification, we turn it into a technical design. How will the system be built? What components will we have? We will go into before to build, but not before we have done design qualification, which is a process of making sure that the technical design actually reflects the user requirement specification. Then software and program development takes place, typically while already doing some unit and integration testing. Integration testing makes sure we fulfill the technical design, all functions are there. Next type of test is a system test, where we see if the system is performing as specified by the system specification. And finally, when the system is put together, we do a so-called factory acceptance test. Then we move the system to our installation, where it's implemented. In implementation, it goes typically through 3 steps: installation, operational, and performance qualification, to make sure the system performs as we want, and at that time is actually ready for production. That's where it's handed over to the final customer, and the customer then will use this system in his production. And obviously, a good user will also ongoingly, continuously monitor if the system is doing a good job and continuously improves it as time goes by. So with this setup, the question is who is involved in doing what? So in a typical setup, you can say that you normally work with a MES subject matter expert team. This team will work on the requirement specification, the system specification, will be involved in system factory acceptance testing and implementing the system. Then we have a second group of users, which is the actual customer. The customer will definitely be involved in the user requirement specification, but also in factory acceptance testing and implementation. And after handover, obviously, customer is responsible for use and ongoing evaluation. And the missing part here is normally done by the system vendor, who is doing the technical design, software development, unit and integration testing. With this setup, you can successfully implement quite complicated systems. So I'm ready to come to the conclusion. We have a setup with a number of systems like TCS, building automation, utility automation, package units. We have LIMS and MES, and we have our historian. They are working together and also connected to the ERP. So the whole vision of automation is not just equipment, but business automation can be fulfilled. When we have this setup, we get as a result not only the product, but reports. We can look at performance dashboards to understand how our plant is doing, and we can do visualizations to see if our plant is operating efficiently. This setup has been used over a long time and has been successful, and it has allowed Roche to produce compliantly Avastin for over 10 years. And finally, I'll give you an overlook. This on the left side, you see the building. Inside here is where this production is happening. And when we have the setup, I just explained in my presentation. Here we have a glance through the windows, the fermentation area. And this has been working now for 10 years and is successful for good health of people who need this kind of medicine. So now I am through, and I would like to thank you for your attention. Goodbye, everybody.